Okay, so these are open loop systems, and our the design design goal, okay, is the first one is we wish the damping ratio equal to 0.5, and apparently this is not, and I will show you. The second one is we wish the undamped natural frequencies equal to 3 radians per second. Okay. So that's the design, and we look into these systems to see how the systems behave. So for this system, we draw the, we investigate the performance of the open loop system here. If this open loop system satisfies this one, then we don't need to spend more time to design the controllers. Okay, so here this is s equal to 0. Then we plot this one. Okay, so from here we can plot the root loci for these systems. So that corresponding, this is k equal to 0 starting from here, and then k go to, okay. And let me re-describe what is this one. So now this is a root locus corresponding to one how do you I think I need to do is this. So this is our GS. And this is our given system. We put the system into a closed loop like this. Okay, so this is C over R. So for this given, this is a given. So given a closed loop system like this, then its characteristic equation C over R will be equal to G, 1 plus G. So therefore, is characteristic equations is 1 plus G equal to 0, or 1 plus 10 and 1s plus 1 equal to 0. Right? So that is the characteristic equations for this. So in particular, you can see this is the plot for this root locus 1 plus k s plus 10, 1 equal to 0. Okay, and now for this given system, we have the value at k equal to 10, right? So from this information, you should be able to determine the corresponding pole. So let me operate here. So corresponding to k equal to 10, you should be, do you know how to locate that one? So basically here is the point. This is a 2 point corresponding to is k equal to 10. How to do it? How do you know which is the location of this point? Easy. You simply solve for s plus 1 plus 10 equal to 0, and this s squared plus s plus 10 equal to 0. So s1 and 2 will be equal to 2a minus b plus equal to b squared minus 4ac, 40. So that is the location of this s1 and s2. Be okay? So from here you can see s1 and s2 basically equal to minus 0.5 and plus minus j and 3.1225. So now we know the locations, so we can see, basically we can plot this. And for this triangle, you can see this triangle. Let me enlarge this one up right here. So basically this location is 3.1225, and this one is 0.5, right? So from this trigonometry, this information, for example, you can use this triangle and to calculate this angle. What is that angle? So this angle is equal to, basically this angle is equal to a cosine of zeta. So you can determine value of the zeta. Definitely zeta is not equal to 0.5. Okay, so you know from this information, furthermore, you can say, you can calculate omega n. Omega n is the magnitudes from this point to the origin here. That's the distance defined as omega n, right? So omega n from this equation, for this case, omega n should be equal to the square of this plus the square of this and take the square root. So that is 0.5 squared plus 3.1225 squared. And for this one, definitely this number won't be equal to 3. No. So by doing this kind of verification, you know this given closed loop system won't achieve this one. Okay? And so now for this case, if we desire have this one, then how can we do? And so this is a design problem, so we can do this. So this is a given, for this figure is a given closed loop system. So that's a figure capture for this. So now, right now for the desired one, we can try to plot here. Okay, so first one from here we defined our desired information. So the angle measured from here is a cosine of zeta. So here we can calculate a cosine of zeta equal to how much? The angle should be equal to 60 degrees.
Mm-hmm.
Is that right? Okay, so basically here we determine this is the 60 degrees. And now we measure 3. So from here to here, the distance omega n. Measure from here to here, that is 3. So here you can locate the desired poles. So from the 2 pieces of information is here. And one is how much? By looking at this triangle here. So if the side is 3, so this one should be 1.5, and this one should be 1.5 times square 3, right? So let me put into that number. That is 2.5981. So basically, desired poles is minus 1.5 plus minus j and 2.5981. Any questions so far? Be good, right? Okay, so this is our desired root. I would say not poles, desired root. Okay. And the other one is here. I think graduate school informed you your thesis is not good enough.
Not even better.
So that is a desired one, and we have original one is here. So what we need to do is this. This is a desired root here, and how can we utilize the concept of lead or lag controller to help on this one? So from here, the thinking is this, because in the given system, this is a given system, okay? And the given system we have shown is not good enough to achieve the desired one. So here we added up the controllers. And let me call this a controller GC. Okay, and then for these sections, we exercise lead or lag controllers. So let me just take the template. I don't know the A and B yet, okay, but I will determine. So basically here to exercise, we pick this kind of the template for a controller. And our goal is to determine the A, B, and K for this case. So these are output, this is the input here. Hopefully, by adding these controllers, we have the closed loop roots, the roots, the poles, the roots of the characteristic equation is here, okay. Under these situations, then we can see what we can do. So right now, I'm going to do is to overlap the two drawing into the single one for us to have a better visualizations. So for these systems, and let me use the color. So this is point 1 and point 2. Let me kind of do the scale. And 1, 2, 3, 1, 2, 3. Minus 1, minus 2, and 1, 2, 3. Okay, something like this. So for the given system, I use the red color. And from the given closed loop system, here we have calculated this is the roots here. Okay, and our desired roots is here. Let me use this color. Our desired root is this one, minus 0.5 and then 2.5 here. Okay, so desired. Here. Okay. So how can we add the controllers such that this blue dot is on the root locus of this revised system. So the thinking is this. Let me call the desired is, say, this point I just give a symbol, okay? I just give a symbol, say S. Okay, so S is the desired one. And then we look at these systems. Right now for these systems, I think here we have those informations ready here, so I can release the space. So for the revised closed loop systems, we can calculate the transfer function that is GC, G, and 1 plus GC, G. So therefore, the characteristic equation is 1 plus GC, G equal to 0, and we can substitute the GC, G into here. So K, S plus A, S plus B, and G equal to 1, S plus 1, no 10, sorry, equal to 0. Okay. This is the characteristic equations. We wish this desired point is the root here, right? So it's back to the first homework in this module. Do you remember in that homework exercise, you have practiced how to verify whether a point is on the root loci or not? Do you remember that portion? If I give you characteristic equations, I asked you whether the following points on the root loci or not. Do you remember that question?
Is that the multiple choice one?
Yeah. So how you complete that question? You simply apply either we have two criteria, phase angle criteria and magnitude phase criteria, right? And phase angle criteria is the way to check whether the point is on the root loci. If the point is on the root loci, then the phase angle criteria must be satisfied, right? So we're using this criteria. So basically for this case, the phase criteria is this. S plus A and minus S plus B and plus S plus S plus 1. And for this is a phase on the numerators, right? And this is a phase on the denominators. The phase criteria, that means as A S over B and 10 times K and S plus 1 minus equal to minus 1 and minus 1 over K, like this one. So that means the phase of this one must be equal to minus 180 degrees plus L times 360, right? So that is the one we know. So use this information to see what happens. So basically S minus A minus S plus B, okay? And we don't know the AB yet, but I leave it open. And let me complete this one. And let me get into this. So what is S? So this one basically is at S equal to the desired. Desired is minus 1.5 plus or minus J 2.5891. So here let me pick up 1. Okay, so the other one will be automatically satisfied. So here I pick 1 for our calculation. So this one, at that point, by adding the controllers, we ask at this point is on the root loci. So that means this one must be satisfied. Good? Okay, so now we can calculate. So what is this one? So that one, this is the S here, and this is minus 1 here. So now we simply calculate this angle. This angle go to here. Is that right? How much? I don't have calculations. What is this angle? This angle basically is 90 degrees plus this one. So let me draw this triangle here. So this is origin, and this is the desired S. So let me draw this one. So basically this is 1.5 and this is 2.5981.
It's 180 minus 60, isn't it?
Yeah, so this is exactly 30 degrees. Because we know this is the 60 degrees. So this is 30, right? So basically this is 120. Are we okay? And now how about this? So this one, let me measure here. So that angle is this one, right? So this angle we can utilize is this triangle. So this is 2.5981, and this portion is 90 degrees. So basically here I'm picking is this smaller triangle. Okay, everyone head up, and I don't want to mess up. Basically this triangle corresponding is this one. Okay, so this one is 0.5, right? So in this way, you can calculate this angle, then you can also determine this angle. So anyone have a calculator, help me punch it. Do it, please.
I got 79 degrees.
79. Okay, so that's why it should be
69 or 79?
79.
79.107.
Okay, so this should be 101. approximate. Okay. So now from this case, you can see the s plus a minus s plus b and minus 120 minus 101 degrees equal to, say, minus 180. Let me here take the L equal to 0. So from here you can see s plus a minus s plus b must be equal to 221 and minus 80, so 41 degrees. Good? So now in the beginning, we select the patterns of the lead or lag controllers. In our calculation, to satisfy the desired information, then we determine S minus and this angle is 41 degrees. Then we check against our definition here. Would that be this case? Right? So here we determine by meeting the design criteria, we know we have this one. So basically that means the contributions from the controller must give us the 41 degrees such that the revised one have go to here. You good? Okay, so that is the one we, basically here you can see from this step, this one we simply apply the fundamental criteria of the root locus here. It's nothing fancy, but we try to integrate the old information to here. Okay? Okay, so now we have determined, so then we simply, that is making the things easy. So leave this behind and we work on this. So now again, from the controller, we simply copy that information. So here for the information, let me copy from there. So for right now, we determine we need a lead controller. Lead controller is, we have the arrangement like this, right? So here is the phi. For example, whatever the symbol you use, phi2, phi1. So we need is phi2 minus phi1 equal to 45 degrees. That is a design goal to achieve, right? So now here you are going to choose A and B. The S here is our desired is minus 0.5 plus J. J how much? 2.5981. Okay. So from this point to there, we have to have this requirement. So right now, it's come to the design, and what you can do is, this is GC. Let me pick up GC as plus B, S plus A. So this is minus B, this is minus B. Okay. So you can do is you simply determine one parameter and then determine that one. So for example, here you might want is say I have calculations here. So here is the options. Option one is you can choose B equal to 1.9432. Arbitrary numbers you pick. If you like, you can pick 2. Okay, so I would say the pick, and then determine A. And so basically using these informations, so that means the S plus A minus S and plus 1.9432 at S equal to minus 1.5 plus J 2.5981. Okay. So simply you determine A is using these informations, 41 degrees. Okay. So how to do it? And basically you simply plug into here. So when S equal to that one simply is minus 1.5 plus J 2.5981 and minus plus A and minus Jesus. this one, s plus a is minus 1.5 plus a plus j 2.5981. So that is s plus a. And so that is this angle, right? So for this angle, basically is the arctangent of the imaginary part, 5.598, 2.5981, and then divided by real part, 1.5 plus 8. Basically, the angle is determined, you want to implement it is in this way, right? Okay, the same thing for this case, and that is minus 1.5 plus j 2.5981 and plus 1.9432. Okay, so then basically this angle equal to arctangent 2.5981, and then that is 0.4432, right? So if you choose the different number of the b, then basically this number will be changed. But anyhow, the two numbers must be equal to 45 degrees. Then you can figure out the a. Okay, so for this case, let me write it down. The a will be equal to, by solving these equations, then a will be equal to 4.6458. Okay, good? So far so good. Any questions? I need you to ask any questions now rather than during the test. And I will give you more information about the test later on. Good? Okay, so that's the one option. Yes?
Question. I'm just plugging that inverse tangent at the end. Okay, good.
Yeah.
Or the last one.
Okay, the last one.
I'm getting 80 degrees.
80.
Yeah.
This one is 80 degrees. Then so basically this one, let me see, I don't have that plug-in here.
Doesn't it have to be greater than 90?
So right now, basically, you're saying this one is 80 degrees, right? This one, right?
Yes.
This one. So basically, that is the one. No, sorry. Yeah, that's true. So for this case, let me plot it. So right now, b equal to here. Equal to minus 1.94 something, okay? So A is somewhere, B is here, and A is here. So now our desired one is here, as equal to minus 1.5 plus something. Okay, so here we really, in terms of the accurate drawing, we are dealing with in this case. So this one you calculated is 80, right? Good. So in this way, this angle must be, this one minus this one is 41 degrees, right? So this one should be 39 degrees. Okay, so that means in this way, this angle must be equal to 39 degrees. Am I right? Any mistake? Holy cow.
Original drawing was confusing.
You see, sorry, my mistake. A, B. Okay, so that is mistake. Yeah, so under this situation, that should everything consistent.
Yeah, and plugging that A value in
Yeah,
there.
yeah. So basically, it's swap, right?
But it works out.
Like this. Good. Sorry about that one. That is my mistake. Picking up the, yeah.
So we are plugging A value or B value?
Here is the B value, right?
After option 1, B.
Okay, so Okay? So anyhow, the key point is you determine one and you guess one and determine the other one. So under this kind of revision, everything should be consistent. So under this situation, then we can get this done. And any more questions? So you can keep playing. So yes.
Can you just pick 0 for one of those?
Yes, of course, you can pick 0, and then basically, if you pick 0, then you're going to cancel 1 there, right? And usually, the cancellation of the zeros and poles is not recommended in the practical controller design. And the reason why is this. Okay, in theory, if we cancel 1 0 from one pole, that can simplify our closed loop transfer functions. But on the other side, if you have chance to learn more advanced control dynamics, cancellation of the 0 and poles representing you're going to hide dynamics. Basically, the hidden dynamics in your closed loop control, you won't be able to directly control it. So you can imagine there's a black box. You can control the black box, but inside the black box there's a fly, kind of free flying. You won't be able to control anything kind of hidden dynamics. That is sometimes dangerous. If this hidden dynamics is unstable, you see you have the closed loop system. You're not able to control this kind of unstable seeds in there. That's dangerous. As long as you guarantee that hidden dynamics is stable, then it's okay to do it. Because that's when sometimes cancellation of whole zeros is simple. Okay, you can simplify the whole thing. Yes, and the answer is yes, you can do it. And but in terms of the exercise or grading, that'll be good enough. But for further things, then I will criticize that one. Okay. So that's the one option. Then you can keep playing for the other options. And so right now, by doing so, we have A, B choose by this way. Then now the issue is how can we determine K value? Right now, we haven't talked about the K value. And to determine the K value here, I want to add it up. Usually, the K value is determined by additional requirement or constraint. So from the example say we have the ES, the steady state error. Steady state error is by how much? Okay. So usually for this case is a certain value. Okay, so certain value, for example, we can set it up the steady state error criteria by many ways. For example, I directly say ESS equal to less than 0.1. Or sometimes we have the options to set it up for example, either one would be good. Say, for example, ESS is less than or equal to 0.1. Okay, and the other example is we set it up this value. If you remember, we have been talking KV is equal to for example, say whatever I would say 10. And do you remember what is the KV? The KV by definition is this. And this one KV is called the I forgot that one, but here the definition is this. KV definition is limit as approaching to 0, and then S, GC, and G. Okay, so KV by definition is this. Then steady state error equal to 1 divided by KV under the unit ramp input. Here I forgot, I shouldn't say this one, I shouldn't provide you the unverified, but basically if you calculate KV, then you can determine steady state error by this. Okay, So usually we can set it up directly by value, or sometimes we can set it up through this kind of the constant. Okay, I think this one, KV, we have three such values. We have defined KP, we have defined KV, and we have defined KA. And for the three definitions, you can go back to when we talk about the system type, the type of the system, and when we talk about the analysis of the dynamic systems for unit step input, unit ramp input, unit parabolic input, that section we have three things defined. Okay, but anyhow, the ESS equal to KV, and ESS equal to 1 over KS, etc. Okay, so here we can have the K to define, and so in this way, under these situations, we can determine. So for yeah, so that is the information here, and I think that's pretty much okay. So I think that's it for this one.